And there are applications, I guess, to large charge. And in fact, some of the early work came because of, I guess, Suzanne and Domenico being interested in this new technique of doing calculations in the lattice, which are non-perturbative. So I just wanted to give you a sort of a slightly different introduction to the whole sort of challenge that some of us are thinking about. And that goes by this name, which we have coined as Qubit Regularization, right? So it's I think even I would say in terms of physics, at least from our perspective, it's an interesting question, and there are lots of maybe even analytic calculations or thought that needs to go into it. So I just wanted to give you that introduction, and then of course give you some recent results that I've done with Debashish Banerjee, and who's I guess in the audience, and I'll tell you a bit about what we find and maybe some of the recent predictions by the large charge collaboration. And then I'll also mention another interesting work that we have just recently done on how maybe asymptotically free theories can emerge in this new way of thinking about quantum field theories in itself. So let me begin. Whoops, I guess I should, yeah. So the outline of my talk is, I'm sure all of you are aware of sort of where quantum field theories arise, but I will just give you a brief introduction from my perspective. And then I will talk a bit about qubit regularization. What exactly do we mean by that? And I will take the O3 model, right? Just the simplest model, which was quite exciting for us, even the simple model, to think in terms of qubits. And then I will explain how this is easily generalized to ON models. And this is exactly the kind of thing that we used in some of our earlier work with Suzanne and Domenico on doing the O4 model. So there we discovered it in a slightly different context, but then we now know that it is a more general way of doing all kinds of quantum field theories, and especially very helpful when we talk about large charges near a CFT. So I think there are many other questions we can study with this approach. And then I will explain to you what the challenge of asymptotic freedom was in this language, and then present my conclusions. So please stop me. It's in my sense, it's a bit long talk, but we can skip portions as we go on. And Domenico, can you please alert me maybe about 35, 40 minutes so that I will know how.
Okay, I will scream at you, don't worry.
Yeah, okay, great. Okay, so let's quickly go through how we think about renormalizable field theories. So from a non-perturbative definition, the way we go about defining a quantum field theory is we regularize it on a lattice. And at the moment, we only think in Euclidean space. So there is a Euclidean lattice, if you wish. And then continuum limits of these lattices are reached by tuning a few parameters. So typically at these continuum limits, the lattice theory approaches some kind of critical point. And so we'd like to understand the properties of these long correlation lengths near those critical points, and then quantum field theories emerge from that. So a continuum limit is typically related to a quantum critical point of a lattice Hamiltonian. Now, whether we get the right critical point, which is the desired quantum field theory, for that we need to be careful about what quantum critical point we have in our theory, right? So typically in a lattice Hamiltonian, there may be many quantum critical points, and we'd like to know which is the right one. And as we go on, we will see that this becomes an important issue. And then, of course, this leads to the concept of universality. So in the vicinity of the correct quantum critical point, Wilson's RG tells us that long distance physics must be describable in the vicinity of some fixed point of the theory, and which is where the desired quantum field theory emerges. So this is what we call universality, that we can reverse this and say there's a lot of freedom in choosing the microscopic model that we have. Right? There's not a single lattice model. We all can come up with our favorite lattice models, and still by tuning ourselves to the right critical point, we should be able to get the right physics. So why not use this freedom? So that's the question that we'd like to understand. So this leads us to this notion of qubit regularization. What this means is, of course, the motivation comes from, there's a big hype these days that maybe someday quantum computers will be available and maybe we can formulate our quantum field theories on a quantum computer and then maybe even do real-time dynamics, which is something that we just can't do at the moment. And so that is sort of the main motivation for these qubit models. But then we would like to understand whether in a qubit way, we can still reproduce quantum field theory, right? That's the whole idea of qubit regularization. So one way to think about this issue is traditional lattice regularization means that we construct lattice models based on our continuum quantum field theory, right? We just discretize space-time, but keep the original quantum fields as they are. But this typically, especially for bosonic fields, has an infinite dimensional Hilbert space per site, right? So qubit models, qubit regularization is one step further. So we don't just regularize the lattice, we also regularize the Hilbert space on each site, right? So we truncate, or we think about the space to be made out of just a finite degrees of freedom for at each site, right? And so then the question is whether these lattice models, which have a finite dimensional Hilbert space per lattice site, can still create back our continuum quantum field theories, right? So are we at the right, within the basis of attraction of the right critical point? So this is an interesting conceptual question and often hard to answer, because once you go into this finite dimensional spaces, all your usual perturbative analytic techniques begin to fail. And so it's not obvious that this is going to work out. So is this even possible? That's an interesting question to ask. So here is sort of a cartoon example of what we are thinking about. So there is some space of all possible models. There are certain irrelevant and relevant directions, right? And so we'd like to study the physics close to this fixed point. And so we can start with a traditional model maybe and tune ourselves to this quantum critical point, and the long distance physics then tells us about the physics close to this fixed point. The question then is, are there other models? Maybe there is a qubit regularization of this model. Maybe each site has n qubits, and that's it. This model had an infinite dimensional Hilbert space per lattice site, whereas here the model is just finite dimensional, right, on each site. But this has maybe all the interesting properties that we want. And so we just have to find the right critical point in this model, and still we'll get the physics of this critical point.
Shailesh, can
Yes.
I ask you a quick question?
Sure.
We go through that. But usually, when you take the continuum limit,
Yes.
you just need to make, well, you just need to make space continuum, right? But here, will you also need to make the degrees of freedom on at each point infinite, or you can keep them finite?
Great question. Hopefully my next slide tells you that, right? Oops, not quite. Where did it go? Yeah, so I guess at some point I was going to get to that. Maybe I will. Yeah, just wait for a few more minutes. Oh, did I lose everything? Maybe I.
Oh, sorry.
Stop.
Sorry, I shouldn't have asked.
No, that's okay. Maybe I should do that first and then share the screen. I guess what happens is, as soon as I say I stop that play mode, it goes into the. So I'll get to that answer in a couple of slides, right? It's a good question. So let me explain to you what this idea is in the simple O3 mod, right? We all know this. So I think it's easy to understand what I'm trying to talk about. So here I'm going to think about X as a d-dimensional spatial lattice. So the time is still continuous at the moment. And so, because I'm going to think in terms of Hamiltonians rather than Lagrangians and actions. So this O3 model is defined by our quantum rotor, right? It's a, if you want to think about it as a particle on the surface of a sphere of unit dimension, unit magnitude. So the variables there are two conjugate variables, theta and phi, or L, right? And then we are going to assume that the particle is on the surface of a unit sphere, so phi dot phi is 1. Now, these are quantum operators, so we write down all the commutation relations. So these are basically angular momentum, so they obey the usual angular momentum commutation relations. Now, phi is a vector, so that obeys the usual vector commutation relation. But in addition, typically in these models, we think that the phi commutes with itself, right? Because these are just positions and different positions commute with itself. So this then defines your sort of commutator space or the Hilbert space of the model. And so we then build Hamiltonians of this type, right? The first thing to notice is that on each lattice site, the Hamiltonian, the Hilbert space is infinite dimensional. So you can write it in position basis, or you can write it in an angular momentum basis. And so the goal now is to extract the continuum physics of this O3 model, which, for example, in 3 dimensions, it has a Wilson-Fisher fixed point. Can we extract that? Or in 2 dimensions, there is this asymptotically free fixed point. Can we extract that using this lattice regularization? And so usually one can start with different lattice Hamiltonians, and this is the old-fashioned universality, right? So the traditional approach would be to start with this Qubit Hamiltonian. That's what we think about on the lattice. So we write down the usual kinetic term and a potential term, right? And then we tune ourselves to a quantum critical point, and this G allows us to do that. So for example, in D equals 2, that means 2 spatial dimensions and 3 spatial dimensions. We can tune G and get to a critical point, and in D equals 2, it will be the Wilson-Fisher fixed point, and in D equals 3 is just the Gaussian fixed point. Now in 2 dimensions, or 1 plus 1 dimension, as I tune G to 0, I get the asymptotically free theory, right? So the physics close to these fixed points, can they be studied using a truncated finite dimensional approach, right? That's the question. So let me quickly briefly mention about the symmetries of this qubit regularized theory a bit, and that sort of gives us some interesting insight into what's going on. So of course, symmetries clearly must play a role when we think about fixed points, right? And so can we construct a local finite dimensional Hilbert space preserving the O3 symmetry, right? So if you go back and look at this example of all the commutators, we want to impose all of these, but if we impose all of these, then we will be led to an infinite dimensional Hilbert space. So something must give way, right? We have to constrain the symmetries, but still relax some relations, right? So this is, of course, a very important relation because that's telling you the symmetry of the model. Clearly, this also is important because then that tells you that the phi is a vector. But perhaps this is not an important part of the symmetry because maybe it's just a unit magnitude. Maybe these are non-commuting observables, right? So that's perfectly okay. And so maybe we can also relax the constraint that phi dot phi is 1, right? These are some things that we already think should be okay to preserve the critical point or the fixed point. So let's do that. Let's define qubit operators by just projecting ourselves to a local finite dimensional Hilbert space. So we'll take our phi and project it to what I call phi q, where q stands for this qubit regularized theory, right? And L will be LQ. And the way we will do that is we will project in the representation space of L, right? We will say, let's project to, let's say, some PL, which is a subset of all possible L's, right? And so then LQ will just be the projector of LA, and QA will be the projector on that QA space. So again, now I just have a finite dimensional space, but I'm preserving, as you will see in a minute, I will preserve all symmetries of the theory because you can show that this preserves the commutators that we want. It does not preserve the commutators we don't want. Right? That's what is going to happen. So now I answer Domenico's question. So in fact, there are 2 ideas, right? One is what we call qubit truncation. So we say, as we thought that the lattice was a truncation or a discretization of the continuum, and you had to take the continuum limit, right? So you had to just go to long distances. So maybe you start with a traditional lattice Hamiltonian, just do this truncation I just mentioned, project it to a qubit space at every point, and you get an n qubit Hamiltonian, right? Maybe the Hilbert space is represented by n qubits. Then one natural way is to think about n going to infinity and a going to 0. This is exactly what Domenico asked, right? So that's one way to think about the problem. In fact, this is exactly the way many people who do I'm sure you've seen papers on quantum computers and how field theories can be done with quantum computers is becoming a very hot topic of research. Many of them take this approach, right? And so this is what I call the particle physics viewpoint, where you say that your original quantum field theory is given to you, right? You discretize it, and then you just go back in some way. However, what we are thinking is slightly different. We are saying maybe there's something more fundamental that we can think about. Maybe we should explore all Hamiltonians in a fixed n qubit space, right? So we don't take n to infinity. And then you look for critical points in this space. Maybe there is a critical point where the continuum physics emerges, even in this finite dimensional model, right? And then at that particular point, we get back what we want. And this I call a condensed matter viewpoint, because essentially what we are saying is we are building a material, right? And we are designing all of our atoms or whatever we want in a particular way and assuming that we can tune ourselves to a critical point there. And in that vicinity, we get back the quantum field theory that we want, right? Now, is this possible or not? I don't know. And that's one of the interesting research challenges for us.
Shailesh, if I can make a comment.
Sure.
Roughly 20 years ago, 15 years ago, there were a lot of people working on what they were calling fuzzy sphere. A fuzzy sphere is literally this thing here with fixed L, if I understand correctly.
Exactly. I completely agree with you. Yeah.
Okay. Just to make sure that I understand.
The connection is exactly that, right?
So, so if I understand correctly, at each point, instead of having an S2, well, instead of having a sphere, you have a fuzzy sphere, and that's the model you're starting.
Yeah, exactly. I completely agree. So from a condensed matter viewpoint, this is just a qubit, right? It's like a spin-half system or a bunch of spin-half systems. From the perspective of what you're doing in terms of the quantum Hilbert space, it does become a fuzzy sphere. Exactly.
Thank you.
Exactly. Okay. So then notice, if you truncate it, you of course are destroying the algebra of the theory. And so what is happening is that you're maintaining the algebra of the angular momentum and the fact that phi is a vector, but these two are no longer true, right? And that of course depends on what relations you get here, depends of course on your L that you're choosing, how to project. So let's take the simplest projection in this case, right? I'm going to I can't sort of build my model with just L equals 0. Maybe I can build my model with just L equals 1. We believe that a more natural truncation is having 0 and 1, because then it becomes a 4-dimensional Hilbert space. And so that will be embedded in a 2-qubit space. So this is sort of the simplest 2-qubit Hamiltonian that we can think about. And can it then recreate all my physics, right? That's the question. Now, interestingly, in this particular truncation, if you go back and look at what the algebra is, the algebra becomes very interesting. You get actually the algebra of O4, right? Not O3, right? So it's like an embedding algebra of the O3. So this is what we call the qubit embedding algebra. So whenever we want to construct a model, we have to choose the right number of qubits in maybe the simplest Hilbert space, and that then gives you a different kind of algebra, and that then tells you what are sort of the qubit, what are maybe the lowest dimensional representation that gives you that, right? So that's the way to think about it. So this qubit embedding algebra for a fixed L, right, you have a different set of commutation relations. And the simplest choice, as I mentioned, will be this 2-qubit space. So with this choice, let's think about models that have 2 qubits and see what models we can write down. So the Hamiltonian will still be invariant under O3 rather than O4 because we want to still explore the O3 space. So a couple of years ago, I did this calculation with my student, and we found that we can think about this 2-qubit space as a singlet, maybe a Fock vacuum of the theory, and a triplet, right, where maybe the particles of spin 1 exist, right? And so I'm going to write down a lattice model of just the Fock vacuum, which are basically objects which are invariant under O3, and 3 objects that transform under the vector representation of O3. And we can write down many Hamiltonians. We wrote down the simplest Hamiltonian, where there was some weight for the particle to be in spin 1 sector compared, or the state to be in the spin 1 sector as compared to the spin 0 sector. And then we had terms where the particle hops around, right, has pair creation and annihilation and so on. So if you write down the simple model, here is a hopping term, right? There's a Fock vacuum and there's a particle, and the particle and the Fock vacuum exchange. And then there are pair creation and annihilation events, right? And these are basically the simplest terms that one can write down. So if you really write this down, interestingly, in a space-time symmetric model, if you wish, we basically get a loop gas, right? And the ON extension was done by Hirsch in this paper. So let's look at what will happen in the O3 case, right? In the O3 case, on a space-time lattice, there will be loops, right? Each loop will have 3 orientations depending on the 3 particles, right? These blue dots here are just Fock vacuum states. So this is a space-time lattice, and we can make it symmetric in space-time. So this is a interesting qubit version of the O3 model, right? In the simplest language. So there will be a weight for this Fock vacuum site, and then there will be the partition function will just count the total number of u's, right? U to the power that much, right? That many Fock states, and then each loop, there are NL loops, and each loop has 3 orientations, right? So that's the entropy factor for each loop. And so this is the O3 partition function. And notice everything is discrete. And in this language, you wouldn't even know that there is an O3 symmetry hidden, right? It's like, it's a very simple way to think about an O3 model. Now, if you want to extend it to ON, all that happens is each loop has a fugacity of n rather than 3, right? And that's it. That's all you want to do.
Shailesh, where did the O3 go here?
The O3, remember, okay, it's useful to remember, this is a singlet. This has 3 particles, right? A spin 1 particle. So it's a vector in spin 1. And the way these interactions go, they're all O3 invariant. And that's how it's O3.
Okay. So loops and the single dots, these are O3 invariant objects. And that's
exactly
what you're counting all the O3 invariant objects, something like that. Okay.
Exactly. And the factor of 3 just tells you that there are 3 states in that O3 invariant subspace. That's all.
Okay.
And if it was ON, it'll become an N space. And that's it.
But you don't care about the size of the loop. You just count the loops, right?
And that comes from the dynamics of the local things. So in a broken phase, these loops have very big sizes. In a symmetric phase, they are very small sizes.
Mm-hmm.
So there is some kind of an interesting transition. And this is exactly what leads to this Wilson-Fisher fixed point in these models.
Okay, thank you.
Sure. So this is where then we come to this application in the O4 CFT. And this is something that we did with Suzanne and Domenico and Debashish.
Sorry, one question before you go to the application then.
Sure.
Yeah, sorry, just I'm not sure, just to be sure the understanding, like this idea of truncating of having a finite dimensional Hilbert space. I mean, what's different conceptually with respect to what we do, say, with the Ising, right? There you have a two-dimensional Hilbert space at every lattice site and take the continuum limit. I mean, is there some?
So this is very similar to that idea. It is nothing different. However, people have not explored that idea for all kinds of field theories. That's all I'll say.
So that for continuous symmetry, it was never explored before. That's the
at least it's hard to say. There are always statistical mechanics models of these loops. I'm not sure. I've looked at the literature. It's not clear that they look at it, at least in this viewpoint. There are papers which say that there is continuous symmetries in these loop models, right? So from the statistical mechanics point of view. So there are definitely connections, but this whole, I would say the idea is now to do it for all field theories, right? Is it possible or not? And how do you do that? And I will mention a bit about that as we go on.
Okay, thank you.
Right. So how is this okay, so this is essentially the same question as Gabriel, but how is this different from a Potts model with the 3 states per site that rotate with the Z3?
So, but notice that the Potts model has a different critical exponents than, so if you really try to use the Potts model to get to the Wilson-Fisher fixed point, you won't be able to do that.
Right. But
so this model does have, exactly. So it has been built in such a way from a quantum Hamiltonian where you can actually see that you have the right symmetries. So you can ask all kinds of questions about that symmetry. If I just gave you this model out of the blue, I wouldn't know how to view this, right, in that language. That's one way to think about it. So in a way, I would say that in this model, many degrees of freedom have been integrated out. So you don't know how the symmetry structure is sort of manifesting itself.
And do you get only the Wilson-Fisher fixed point for this thing? I mean, are there different?
Yeah, we'll come back to that. It's a good question. That's the last part of the talk. I will. There are lots of interesting things we are learning. I think these are all excellent questions. I'm going to come back to that in a minute.
Thank you.
Yeah. So we are learning. Remember, this is not something that I'm just learning. So I'm sure new interesting questions would be interesting to ask. Okay, so let me quickly tell you, we have some new results, and I'd like to tell that because there's a large charge audience, and so it'll be good to see where some of these techniques are applicable. So let me quickly review the application to the O4. So this is something that we already did with Suzanne and Domenico and Debashish. So we wanted to sort of study this Wilson-Fisher fixed point. As I told you, in this approach, you will need a 5-dimensional Hilbert space, one for the Fock vacuum and one for the O4, 4 for the O4 vector, right? And so it's a Hilbert space which has 5-dimensional Hilbert space. And so that will be a Fock vacuum state. And then there will be 4 vector states which transform under the, so this will be important. I will assume that the O4 is written in terms of SU2 cross SU2, right? And so talk about the L and the R sectors of SU2. And so the vector is a half-half. So these 4 states can be given these quantum numbers, half-half, half, depending on how you want to think about it. I've just written down some Z component quantum numbers. So notice in my loop model, there will be 4 states, and each of those 4 states will have quantum numbers of this type. And how do you recognize that? Go back to write it in the qubit language, and then you will see what this is. Now, of course, you can write down the Euclidean partition function. As I just mentioned, there will be a u to the power k, count the number of Fock states, right, times 4 to the power of NL, right? That's the way to think about it. So each loop has now 4 orientations. Here I write it in terms of...
I'm sorry, can I quickly ask a question?
Sure.
About the last page. Why do you not have things like with JL equal to 0 and JR equal to 1/2?
Yeah, so you can have it. So this is, remember, there are lots of interesting ways to write this model. So in our qubit regularization, the simplest was, because it was a vector model, right? If you start with the O4, you start with a 0, 0, and the next was a half-half. you don't have a 0, half, and a half 0 in your original model.
If I may, Raphael, the difference between representations of O4 and SU2 cross SU2 is precisely this.
Exactly.
In O4, you only have those that have the same variance.
Yeah, so you could, in fact, there are condensed matter models where you do have 0, half, and half 0 as states, right? And in that, the half 0 and 0, half can combine to make a vector. And so you have, the model space is much richer, right? And so there are, in fact, many more interesting critical points. And this is something that condensed matter physics is often used, right? Because, for example, the Hubbard model is like that. A spin half, if you write down a spin half particle on a lattice, you can show that the model actually is O4 invariant because there are a spin and a pseudo spin fields. And if you want, we can get into that later on. But there are models of that type, and there are fixed points which are different from the O4 fixed point we are interested in. So here the goal was to reproduce the O4 fixed point. And so that's all we did. We said, let's take this qubit regularization. Okay, so the Euclidean partition function is pretty straightforward, right? And we can even measure correlation functions. For example, here, notice, here all are loops, right? Everything is a loop. It's all invariant. Here there is a source and a sink. So by introducing sources and sinks of these O4 particles, we can actually look for O4 correlation functions, right? And this is exactly our trick, that we are now going to put in many charges of O4 and many sinks, sources and sink of O4, and write the right combinations of them that lie in a particular charge sector, right? And then we look at the 2-point correlation function. So that's pretty technical. So I'll have to go through all that. Given the time, I'm not going to get into that. I've also given another talk on this. So if you want, I'll be happy to talk about more details of how we do this. Now, the observables, of course, in our model, at least initially, we just said, let's check whether we have the Wilson-Fisher fixed point in this case. And by measuring the usual susceptibility, there is something called a winding number susceptibility. These obey the critical exponent, the critical relations of the Wilson-Fisher of this type. And our model very beautifully reproduces these things when we tune ourselves to a critical point, right? And so you can actually compare our results with the results in the literature, and they match extremely well, right? So this convinces us that we are actually doing, even in this reduced space, like maybe this is, somebody asked this question, this is like the Ising model version of the O4, if you wish, right? Now, I quickly wanted to say that there's also a fermionic realization of this model. I won't have time to go into that, but we can then use this fermionic realization to actually do the large charge sector much more nicely. Basically ask ourselves how to construct these sources and sinks that transform in a particular representation of RO4, and which was pretty interesting and illuminating. So I'm going to assume that we can do that. Here is a source and a sink in a particular JLJR sector, right? And then that's the correlation function, right? Between X and some 2 points on a lattice, right? And this is supposed to grow as or fall down as a power law, and this D is the conformal dimension in that sector, right? At the Wilson-Fisher fixed point. So we can tune ourselves to UC, the critical point, and then we can measure the 2-point correlation function with different charges, right? So the large charge prediction, as you all already know, was done by Suzanne and Domenico and others in this paper, and they found a very interesting expression, which we then confirmed in this PRL. And what was amazing to us is that even till small j's, right? This is j equals half. In fact, if you dig deeply, there is a small discrepancy here, but it's really beautiful, right? The large charge expansion really works beautifully in this thing. And this was the thing I guess Domenico mentioned at the beginning of my talk, right? So this is an old result. The question is, what happens in the subleading sector, right? And so in the subleading sector, the JL and JR are different. And so we go to one less and then ask what is the difference between these two critical exponents. And this is very natural for us to measure in our approach, right? So we can say we look at the JJ sector, we have a correlation function, and then we change just one spin, right? We can change it everywhere in our source, but that by changing that one spin, we can actually measure a new correlation function that will actually measure, it will decay based on this exponent, this conformal dimension. And so here is a prediction, which I guess came out last year, of how this should behave. Domenico, you can correct me if I'm wrong, but according to your prediction, it seems like this thing will go to 0 for large J. Right? That's what my reading of that result was. Right?
I believe that also Gabriel has some unpublished results that go exactly in the same direction.
Okay. So this is what we wanted to check, right? Because it worked so beautifully in the other leading sector. So we wanted to, now this will be a new constant, so that's fine. So all we want to do is make sure that it goes like 1 over J to the half and figure this out. To be honest, we had a lot of data even before, but Debashish and I did not quite agree on our errors, right? We had lots of fluctuations. This was already, what, 2 years ago now? So this is what happens when something doesn't work in a computational method, by the way. So you are stuck and you have to figure out, and then of course you're distracted by other projects. So finally, I think we are beginning to understand what our errors are, and we are able to reproduce our errors much more efficiently. So let me tell you what the new result here is, right? So these are the latest results from last week.
One question, I think you already asked you in the past, I remember. There is also a prediction, I think, for some Domenico and Susanna concerning the spin of these operators. So not the spin under the internal of 4, but the spin under the space-time rotations. Okay. There is is there a way to say anything about it?
Yeah, good point. So here I think we are only, it's a good question. Maybe we have to be a bit careful about what we are measuring, because we are on a lattice, so we break all kinds of space-time rotations, right? So space-time symmetries are much more trickier. My claim would be that these are like the spin 0 sector of the space-time, because we don't have anything specific that sort of picks out one direction or the other, right, in our sources. So our sources are, although they are distributed on the lattice, we believe that it's like there's no spin structure apart from the O3 structure. Now, this is an interesting question. I think a bit more technical, we can talk about maybe later on.
Okay.
Okay. So just for the little history, what Gabriel is alluding to is that we think at least that these states should have a space-time spin. They shouldn't be scalar.
I mean, there are also scalar states, right? Because there are
also scalar states.
Right. So
I see. So maybe your prediction is not for. So is it true that your prediction is not for scalar states then?
There are both scalars and no scalars, and I think there is in fact a huge degeneracy of state, which has this scaling that you are displaying here. So that was going to be my next question: if you think you can pinpoint a single operator, or the fact that there is a degeneracy of state.
So I think I would say right now, I don't think I will be able to answer your question completely, because we'll have to sort of dig into these spin sort of quantum numbers, I would say, or space-time spin quantum numbers. But for the moment, let me just tell you the results, and then we can think about that. Yeah. So the results are as follows. So these black dots are our new results, which I think we all believe are errors now, right? And these are the various fits to our data. Right now, we have gone only up till J equals 10. And we were hoping that J equals 10 was sufficient, right? So let me tell you what are the various fits that we have. So the first fit was the simplest thing. We said, let's see how far can we go with just the leading J 1 over root J. So you see, that's this yellow line. Not much, right? So we just can fit maybe these three numbers, which is not quite fair. I think this is not good. The next thing we can do is we can put an extra, the next order correction. So clearly what we learn is that in this J space, we will need the next leading order before, or subleading order in J, before we can even make any sort of solid connection, right? With that, indeed, actually we get a reasonably good fit, right? But then of course it starts behaving bad there, but that may be just the artifact of sort of this extra term, right? So all this says is you need this extra coupling, which is negative, and so it sort of starts going down. Just for our own sort of interesting thing, we said, maybe let's say the large charge group has missed a constant, right? Now this is provocative. So let's say we do a fit to that form. And that is this blue line, right? And that blue line also fits roughly in the same range as we are able to fit. So these two are reasonably good fits in the same range, right? So the blue and the green, I would say, are reasonably good. The red is, of course, one more extra thing, and that, of course, allows us to go a bit more, and then we can do that, right? So that's sort of the current state of affairs. Now, if this constant is forbidden, that would be interesting, right? Because I think right now we're just starting some runs at 20. The unfortunate thing, what we realize in this thing is that as you make J larger, our sources have to be expanded, because remember, each of them are just made out of single qubits, right? Or a few qubits. So as J becomes larger, our sources become extended. And this maybe is related to the spin structure of the thing also. Of course, we try to make it as symmetric as we can, right? But of course, it will have some asymmetry. But then as you make this larger, we have to make the lattice size also larger. So these lattice sizes were obtained by 160 squared, right? That was sort of the biggest we could go. It also requires a lot of statistics. So it's like if I start something, it takes almost a month to get one of these data points, right? So now this will require, extra work. So that might really distinguish whether the data lies here or there. Let me just tell you, my old data, which I don't believe my error bars completely, was here, right? So something to think about, and something we can discuss, I guess, after the talk. So let me go on. So that was the first application of this qubit regularized way of thinking about things. Now I want to tell you a bit about asymptotic freedom, which is also a very interesting question, I think, theoretically, and maybe somebody here using this fuzzy sphere language can have something to say about this, right? So we wanted to ask, notice that it is much easier to get IR physics than the UV physics in all of these theories, right? So you just tune yourself to a critical point. Once you have a long distance physics, you can just block yourself and say, well, what is the critical point you have? So getting the Wilson-Fisher fixed point is much easier. However, to get asymptotic freedom, you don't just need, you actually need an UV fixed point, right? In a sense, we want a theory which is free in the ultraviolet. Now in the ultraviolet, we have a lattice. What do you mean it's free? It's not free. So we need to have some kind of a way of checking that we are actually getting the physics, not only in the infrared, but also in the ultraviolet, where the ultraviolet scale is going to be much bigger in that length scales than the lattice, right? So it's a much more tricky and complicated thing, at least numerically, right? So there are three scales, if you wish, to reproduce in this case. One is, of course, the lattice case, lattice spacing, where there are qubit models. So there are n qubits here. And then when you block the system, you get into the ultraviolet scale first, right? And that ultraviolet scale then tells you that the theory is almost free, right? But then that cannot be true all the time. So then there are infrared scales where you get a mass gap, right? So this becomes a very complicated, at least computational problem. So how do we show that all these physical scales, remember the physical scales are not only the mass gap, but all of these various scales that arise as the coupling constant flows, right, to the UV. So we need a way to quantitatively study all these scales and show that we are going to really reproduce the physics. So this has been done in lattice QCD, right? In fact, in the O3 model was the first study. And this is what is called the universal step scaling function, which is something maybe many of you already know about, but let me quickly review. So the goal here is to look for a dimensionless, physical dimensionless coupling, which I define as a mass scale at some lattice size. So I need to define what this means. This is not the infinite dimensional mass, infinite lattice mass scale. It's not the mass gap. This is a mass gap that can be defined on a finite lattice, on a finite physical lattice, right? That times L gives you a very natural dimensionless coupling, U. Then what I can show is that if I calculate, for example, this quantity, right, at some particular in some particular calculation, if I increase my lattice size by an S-fold, that's the scaling, right? Then there is a universal function that tells you what will be the new U, right? So just by increasing my lattice size, notice that L will change, but ML also changes, right? And how that changes is captured by this function sigma. And that sigma is what is called the step scaling function. Now, in an asymptotically free theory, you can actually compute it in perturbation theory, right? And this was done by these authors, right, long ago. For the O3 model, we know what is this, what is that, and so on. And you also know it in the other regime, just from simple scaling arguments, you can show that since the mass is going to go to a finite number, there's a mass gap in the limit as you go to the infrared, then this thing this goes to a constant, this goes by a factor of S. So this goes to S times U, right? So we know how this function behaves in the two limits. Now, instead of the mass, we can also use a correlation length. And so there, usually you define L by C of L, which is U, right? And then you can actually define this ratio of the correlation length at 2 times L by L, right? And that goes like that, just simple algebra there. We know the limits. And so if you plot this with respect to that, you get a universal function, right? Which goes to 1 for small values of this and goes to 2 at large values of that. And this function at other places is non-perturbative. You can actually get a perturbation theory that will go like that. And then you have to get this whole function correct. Now for the traditional model, this thing was calculated using what we call the second moment definition of the correlation length. I can go into the technical details if you want, but here is the result, right? This was again, notice 1995. It's an old result in the O3 model. So this black line is a universal curve of the O3 continuum O3 model obtained using the traditional lattice model. So the goal for us is, can we reproduce this using qubit models, right? Just the 2 qubit model. So we try to do that. I won't have time to do. So all of this was done using what I call the Dca approach, which is one of my collaborators' invention, where we said how to do this using this kind of regularization. However, in that approach, what we had to do was introduce a layer, an extra layer or a dimension. And as we make the dimension larger and larger, we could have reproduced the asymptotic freedom. And there are excellent papers by Uwe and collaborators where they show how the asymptotic freedom of the CPN model is reproduced in that language. But there's an extra layer, notice. It's not like a fixed qubit. Now, if you think about the O3 model, you might say, well, let's take this traditional model, right? We know that traditional model has a continuum limit. Can we just truncate this model and get asymptotic freedom? And this paper actually explored that possibility. And notice with 2 qubits, there's a mass gap, and the mass gap doesn't scale at all. It's far away from what you really want. So just simple truncation will not work, right? So you have to explore the model space a bit. So you're fixing yourself to 2 qubits, but you're exploring the model space. So we tried our favorite loop gas models. Remember, we already talked about the loop gas model. We just now do it in 2D. And we made ourselves an extra variable here, Wx, right? Which is not just the hop on a lattice, but it's like a diagonal hop. This is just changing the model, right? And we're going to explore this space. And so here are the results on the Monte Carlo with 512 lattice sizes. So notice this is the theory that we want to reproduce. The simplest model doesn't do quite well. Notice it comes out of that curve and then maybe merges that curve at around this point, right? So what we would like is to get this part of the curve, which is where the asymptotically free fixed point is. Notice that if I tune myself, I can do better, right? But never am I able to get to this. So these loop gas models were not very helpful. They were very good because you were able to get up to this point, which means they're almost asymptotically free because it's like a good, very good effective field theory, but not, we don't have a fixed point there. There's no continuum limit. So then we explore all kinds of model spaces. So here is the most general model space we can write down. Qubit 1, qubit 2, that's your one dimension, right? Write down all kinds of interactions which are SU2 invariant or O3 invariant if you wish. We have to tune, by the way, these are all Hamiltonian models to match. We have to
just one thing. You asked me to remind you when it's 5-10 minutes.
Yeah. So yeah, I'm almost there. So I think hopefully it'll be fine. So we tried to do that. We measure. I will sort of skip the technical details. So here is the first thing we tried. We tried some spin ladders, right? So we know that if we have 2 spin half ladders and couple them, in the limit, as this JP goes to 0, we actually get 2 spin half ladders which are decoupled, which actually go to the Wess-Zumino-Witten fixed point. It's like a doubled version of the Wess-Zumino-Witten fixed point, right? So this is not the model we want, but we wanted to see maybe the coupling somehow magically takes us to a different fixed point, because now there are 2 of them, right? You're coupling them. And so we tried symmetric and asymmetric ladders, right? And the goal was to explore the physics of JP goes to 0. Remember, that's where the mass gap is generated. And so as I make JP tends to 0, I will have a quantum critical point. And so we tuned our function, and here is the step scaling function. It's terrible, right? It just doesn't work, right? So this is one of the things I think somebody asked, are we sure we will get the right critical point? Most likely not. You'll have to work, right? You've got to work hard. It's not obvious that you're going to get the right critical point. So interestingly, in the literature, no one had figured it out. In fact, Uwe mentioned that maybe we may not even find it, and that was a possibility. So we just gave up. Now here is a model that actually works, right? This is what is called the Heisenberg comb. We call it the Heisenberg comb. So what we have to do is take a spin half, and at each site, just couple it to the second qubit with some coupling, which is of order 1, right? This J is the coupling between the spins on the chain, right? So you can see a comb here. That's the side, and these are the things of the comb. So here is the model. This is set to 1. This is J. And then the quantum critical point is J tends to infinity. Again, it seems like we are getting the critical point of the Wess-Zumino-Witten theory, but it is not. And as I will show you some data, we actually get back the O3 model. So here is, so again, we have to tune some things to get that. Here is the step scaling function, right? So these are the different values of J. Notice for small lattices, at let's say J equals 3, we are not on the curve, right? But as you make larger and larger, think about it like RG blocking, you come back and start flowing on the line, right? Now, as I make J larger, I'm able to go to much. So of course, again, I start some in a strange place. I have to block sufficiently, right? Before I start falling on that curve, and then it starts flowing there. Now, if I make J even larger, I can push the place where it starts turning. So you see, I've created the 3 scales I'm talking about. This is the lattice scale. The place where it starts merging with this line is the UV scale. And of course, reproducing this whole curve is the IR scale, right? So we can actually see where are the 3 scales coming. So how big a lattice do I need before I start getting onto this line? That is what we call L min, right? Now that L min grows with J, and it should, right? Because as J becomes larger, we are going to the wrong fixed point. But then we'll have to block it sufficiently before we start flowing to the right fixed point, right? It's like a UV fixed point. So it goes like that and then comes back and starts flowing correctly. And so the infinite L correlation length, of course, is very large. And so this is like the mass gap, or the infinite 1 over the mass gap of the theory. And this is the UV scale. So notice we are able to reproduce the scales that we really want. So that is, I think, the first example, as far as I know, where in a a finite dimensional qubit model, 2-qubit model, we were able to reproduce asymptotic freedom completely, right? But then we had to search for the model space. It was not easy. Okay, so let me conclude. I think I'm right in time, hopefully. So I believe that the qubit regularization is a useful idea. It is, I wouldn't say it's sort of a completely new idea, because as somebody pointed out, we already know that field theories, at least the infrared fixed points, can be reproduced by doing some kind of truncation of the Hilbert space, right? The Ising model is an excellent example. But as far as I know, that idea has not been extended to all kinds of continuous symmetries and all kinds of field theories. What we are proposing is that that's a idea which is very general. It should be doable for maybe almost all field theories. It'll be very interesting to ask if there are quantum field theories that cannot be done in this way. That'll be even exciting. The first example that came to mind was maybe the asymptotic freedom will not work. And as I just mentioned, it does work, right? So the question is then, what is the smallest number of qubits per lattice site that is necessary to reproduce a particular quantum field theory? Is there a critical point in that space of couplings, right? We also showed that there are interesting applications, especially the large charge studies of CFT, I think, will be done much better using these qubit regularized models. So I do believe that the community that you all are interested in should benefit from this progress. And then, of course, finally, asymptotic freedom, which was sort of, in my opinion, very difficult because you needed a Gaussian integral. I didn't know how to get a Gaussian integral with just 2 qubits, right? It was hard. And this is back to the miracle of RG. And here I really see the miracle of RG in all its glory, right? You start with 2 qubits, you preserve the symmetries, and then if you find the right critical point at large, when you block the system for large enough lattices, you get back the free theory. It's amazing. So, and let me stop there. Yeah, thank you.
Okay.